In this video, we're just going to compare the two main organic curly arrow style mechanisms that we do in the first year of A-level chemistry. So that would be our electrophilic addition and nucleophilic substitution reactions. So electrophilic addition. We're going to start looking at something that might be considered more traditionally an electrophile, so hydrogen halides, in this case hydrogen bromide. And the reason that we can more clearly see that hydrogen bromide is an electrophile is because, of course, it is a polar molecule with a dipole and the hydrogen being delta positive and the bromine being delta negative. And that means that when it draws close to the carbon-carbon double bond, that region of electron density, that pi bond, remember those electrons above and below, is going to start to attract towards the hydrogen. So we've got area of electron density here within the bond, which is what our electrophiles are attracted to. But remember, the second part of our definition of an electrophile is that it accepts a pair of electrons. So in terms of curly arrows, our curly arrows start where there is a pair of electrons and they move towards an electron deficient area. So we are starting in the bond and moving to the hydrogen. We don't want to go from a bond to a bond because that would be moving a pair of electrons into another pair of electrons. But what that does, of course, is if we're going to form a bond with that hydrogen needs to lose the pair of electrons that are being shared with the bromine. And so we show another bond being broken. This time we're not moving towards an area that is electron deficient because we're going to form a negative ion. So this is the way the bond was going to break anyway, in terms of the fact that it was already polar, and so the electrons were already moving towards the bromine. The double bond is, the electrons from the double bond are just pushing that reaction to happen and that bond to break. So two curly arrows showing two bonds breaking. We're breaking the pi bond, so just half of the double bond, and then we're breaking the bond between the hydrogen and the bromine. And so if we are to draw the product of this, which of course is not the full product of the reaction, then the hydrogen is attached to one of the carbons, and I'm not considering asymmetrical alkenes at the moment, so it doesn't matter which carbon we're going to put it on. And then the remaining carbon. So if we looked at this in a dot and cross diagram to explain what's going on, that carbon on the right hand side is sharing currently two pairs of electrons at the start of the reaction with the other carbon. So what's happening is that this bottom pair of electrons is being moved around to form this bond here with the hydrogen. And so the carbon on the right was sharing one of its electrons, and that's been taken away. So the carbon on the right has ended up with fewer electrons than when it started. So this is a genuine positive charge. This is not a delta positive. This is not as a result of a dipole. It's a result of an entire pair of electrons moving from between those atoms to being between these two atoms. And then the bromine, if we were to draw the hydrogen bromide in terms of dot and cross diagrams, then you can see that what's happening is when we break this bond here, we are giving the bromine the electrons that belong to the hydrogen. And so therefore our bromine is becoming a bromide ion. And again, that is a genuine charge and not a delta minus, which means that we can have a curly arrow going from the bromine straight to, or the bromide, straight to the carbon. So a couple of things to note. I've drawn a lone pair on the bromide, and that's because we should be moving bonds or lone pairs when we do curly arrows. So curly arrow is a pair of electrons, so it should be coming from a bond or coming from a lone pair. Obviously that bromide ion actually has, if we look at it, 4 lone pairs because it's got a full outer shell, but all we need to worry about is just drawing one. Doesn't really matter where we draw it, quite often it's drawn next to the negative charge. That's fine. And once our arrow has been drawn, we've basically made our product because we've made a bond between the bromine and the hydrogen. I'm not going to go into the possible alternative products. If you had, for example, an asymmetrical alkene, not all exam boards go over that, but I may include some questions on it. One of the first electrophilic addition reactions we ever learn about, we learn it at GCSE, is of course the addition of halogens such as bromine across the double bond. It's also our test for alkenes and unsaturated compounds. So the only real difference here is simply that bromine is not a polar molecule because of course it's two of the same type of atom. So there's no difference in electronegativity here. However, if we remember that the shape of that pi bond between the two carbon atoms is a large area of electron density, so it's a large cloud of electrons above and below the two carbons. So when a bromine molecule, which is itself has a very large electron cloud, being quite low down in the group, it approaches that pi bond, then what's going to happen is that the electron density in the pi bond is going to repel the electron density around the molecular orbitals of the bromine and is going to therefore induce a dipole across that bond. And so it is just as accurate to draw exactly the same dipole as we would if we were doing a hydrogen bromide instead. And from that moment on, everything else about the mechanism is the same. So we start in the double bond with our curly arrow, moving towards the bromine because it's a delta positive, forming a bond with that bromine atom. This means that the bond between the two bromines needs to break and we form a bromide ion. In our intermediate, we have one of the bromines attached and we have a positive charge, not a delta positive, but a positive charge on the remaining carbon. We have a negative charge on the remaining bromine and we draw our arrow. So all of the other curly arrows are identical. And you may also get questions about how we know this is the mechanism, and your exam board might in fact want you to know that the product of addition of bromine and aqueous bromine, so bromine in the presence of water, is in fact not the one pictured in the bottom right. And you may be asked how this product forms instead. So this is an alcohol with a bromine group in it. And the reason for that is that if you are adding bromine in the presence of water, water dissociates slightly to form hydrogen ions and hydroxide ions. And so hydroxide is present in the solution, which means that this carbocation intermediate, this positively charged intermediate, can in fact be attacked by a hydroxide ion instead. And that is when we would end up with this product over on the far left. Even if it's not explicitly talked about in your exam board, it might actually be mentioned as a sort of more of a stretch and challenge question as to how it's evidence of the mechanism. So it's evidence that a carbocation forms, it's evidence that both bromines don't join on at the same time. So nucleophilic substitution. These are going to be reactions of alcohols and halogenoalkanes. They undergo nucleophilic substitution, substitution because they're saturated and therefore can't undergo addition, and nucleophilic because they contain a delta positive carbon bond. So I'm going to start looking at if we had a negative ion substituting, because that's the easiest mechanism that we can draw. And in fact, nucleophilic substitution is slightly shorter and easier to draw than electrophilic addition if you're going with an anion, such as hydroxide ions, which can attack the positive carbon as a nucleophile. So we want to draw our dipoles. That's a polar bond. So this time the dipole is in the organic compound and not in the attacking molecule. The attacking molecule in this case is the hydroxide ion. So we're going to draw a lone pair because we're going to start from the area where there are most electrons, which of course is my negative ion, and we're going to move to a delta positive. In order to make a bond with that carbon needs to lose a pair of electrons in order to accept the electrons from the hydroxide ions, and it does that by breaking the carbon-bromine bond and forming a Br-. So in fact, if we use a negative ion to attack our carbon, then we have everything happening in one step and the whole reaction is finished. When you do rates of reaction, you may very well learn that there are in fact two different ways that this mechanism can take place. So I've called this one that happens in one step, where the hydroxide ion comes in at the same time as the bromine comes off. You might actually also learn about the bromine coming off first, leaving a carbocation, and the hydroxide ion going in. But the curly arrows are the same. It's just whether we draw them in the same part or whether we draw them separate one after another. What students often find more challenging is when we have a nucleophilic substitution reaction where the nucleophile does not have a negative charge. So for example, water is perfectly capable on its own of breaking, hydrolyzing that carbon-bromine bond and substituting. But the mechanism is just very slightly different. And so my water molecule has two lone pairs, but I'm only going to draw one because that's all I need. And there is no difference in the first step of the reaction. So the first step will be that the lone pair on the oxygen is attracted towards and donates to the delta positive carbon, and for that new bond to form, we therefore need to break off the bromine as a bromide ion. So the difference here is that I now have a whole water molecule attached. It would be a dative covalent bond, but we don't tend to draw it like that because it's just a normal covalent bond once it's formed, to the carbon. Now, looking at charges, if I look at the right hand side here, my bromine has a minus charge, so that's a bromide ion, and that's because the electrons went from the carbon to the bromine. So what does that mean about the remaining molecule? There must be a positive charge somewhere. So the electrons went to the bromine from this bond here between the carbon and the bromine. So that carbon effectively lost an electron that it was sharing. And so we can actually consider, and this happens sometimes in alternate mechanisms, that we've made a carbocation. That is the thing that the water molecule has donated its lone pair to. So having donated its lone pair, the carbon is now fine because it's now got back the electrons, but the oxygen has now got a positive charge. And again, this is a genuine positive charge, not a delta positive, because the oxygen is basically as if it were forming a dative bond with H+, then you would draw the whole molecule as H3O+, and that's the kind of thing that we've got going on here. So the oxygen is donating electrons and therefore ends up electron deficient itself. The way that it gets those electrons back, well, we're going to form an alcohol. We're not going to form a different product simply because we're using water instead of hydroxide. And so the way that we get rid of the positive charge is we lose H+. So the electrons that are being shared between the oxygen and hydrogen are both going back on the oxygen to give it back its lone pair that it's currently donated to form a new bond with the carbon. And then we're left with H plus and Br minus, and so often it's shown as the Br minus attaching to the H plus. In reality, in aqueous solution, the HBr would be dissociated. You'd have a separate H plus and Br minus ion, but we would tend to write it as HBr in the balanced equation just for simplicity. So it's always helpful if, instead of rote learning, we try and look for similarities and differences so that we don't make careless errors with our mechanisms. So looking at the two mechanisms that we've covered so far, what are the similarities and what are the differences? Well, both mechanisms are going to start with a polar molecule, some sort of dipole that is going to encourage the movement of electrons. Both of them are going to have a pair of electrons moving from an area where there is a spare pair of electrons in towards a delta positive. In the electrophilic addition mechanism, that spare pair of electrons is the pi bond, and in the nucleophilic substitution reaction, the spare pair of electrons is a lone pair on the nucleophile. Other differences is that in the electrophilic addition, the dipole is on the electrophile, it's on the thing that is not the organic molecule. In nucleophilic substitution, the dipole is within the organic molecule and it's a positive carbon. But other than that, the direction of the arrows is from the area of electron density towards a delta positive. So we have those similarities. Second similarity is that in order for that new bond to be made, another bond is broken. In both cases here, we are making a bromide ion. Of course, it could be something else. It could be chloride. It could even be an OH minus. Same idea though, a pair of electrons is moving towards a delta negative, so where the electrons were already being attracted to because of the electronegativity of that atom. So other thing in common, of course, is that both of these first steps have two curly arrows. So there are lots of things that are similar about them. Another thing to notice is that if you are using a neutral, uncharged nucleophile, both of these have a positively charged intermediate. The difference is in how we resolve this positive charge and get our neutral, no charge overall final product. In the electrophilic addition mechanism, we add. That makes sense because we're doing addition, so the negative ion adds to the positive charge. Because that carbon is positive and it doesn't have enough bonds around it, it's only got 3. And in the nucleophilic substitution reaction, so this time I've chosen ammonia just to give you a different example. In this case, we lose a positive ion. So on the left, we're gaining a negative ion because we've got not enough bonds as well as positive charge. And on the right, we lose a positive ion because we've got too many bonds around my nitrogen. And therefore, we're going to lose a positive charge in the form of H plus. So it's important not to just rote learn mechanisms, but to try and consider why the arrows are moving where they are and why the charges are ending up where they are. That will really help you in the second year when you start to look at nucleophilic addition and electrophilic substitution, and also when you might get given questions that involve unfamiliar mechanisms. So don't always assume that a mechanism question will be a mechanism that you've seen before.